Hello students, welcome to BTech first year bridge course. In the last lecture, we have discussed about electrostatic boundary conditions. Today, we will discuss electrostatic energy of discrete and continuous charge distribution. Now suppose we have a stationary configuration of source charges. Okay, so these are point charges. And we want to move a test charge capital Q from point A to point B. Now the electrostatic force which is applied on Q due to configuration of these discrete point charges is Q multiplied by magnitude of electric field due to these discrete point charges. Now as the charge Q is positive in nature, the force will be applied along the direction of the electric field, which is along this outward direction. So here we are considering these charges are also positive charge, right? So the electric field direction will be along this outward direction. Now to move the charge Q from A to B without any acceleration, we have to apply same minimum force opposite to the electrostatic force, which is minus of Q multiplied by magnitude of electric field, right? So the work done is represented by this equation, and we get work done as charge Q multiplied by the potential difference between B point and A point, right? And we get potential difference is equal to the work done per unit charge required to carry the charge particle from A to B point without any acceleration. Now, if the reference point is set to infinity, then the work done will be Q multiplied by the potential at the particular point where the charge is kept finally, because the potential at infinity is 0, right? So this is the work done to move the charge inside an electric field, and it is stored as electrostatic energy in the system as potential energy. Now let's discuss how much work would it take to assemble an entire collection of point charges. So the first charge Q1 takes no work since there is no field to fight against, right? Now to bring in Q2, work done is this. Here 1 by 4 pi epsilon naught Q1 by R12 is the potential due to Q1 charge at Q2, right? Now to bring Q3, work done will be this. Here 1 by 4 pi epsilon naught Q1 by R13 is the potential due to Q1 at Q3, and 1 by 4 pi epsilon naught Q2 by R23 is the potential due to Q2 at Q3, right? Similarly, to bring Q4, the work done will be this, right? So the total work done necessary to assemble the 4 charges is the addition of W2, W3 and W4, and we get this form, right? Now for n number of charges, total work done to assemble will be like this. Okay, here J greater than I is written because it is just to remind you not to count the same pair twice. Okay. Now a nicer way to accomplish the same purpose is intentionally to count each pair and then divided by 2. Okay, so that's why this 8 is coming. And we get this equation. Now let's pull out the factor qi and we get this form. Now the term in the parenthesis is the potential at Ri, which is the position of qi charge, okay, due to all other charges. So this is how much work it takes to assemble a configuration of point charges, n number of point charges, and this work done is stored as electrostatic energy in the system. Okay. Now let's discuss electrostatic energy for continuous charge distribution. For volume charge distribution, the work done from this discrete form can be written like this. Okay. Here this rho is the volume charge density. Now this integral for line charge will be lambda v dl, where lambda is the charge per unit length. For surface charge, this form will be sigma v dA, where sigma is the surface charge density. Okay. Now using differential form of Gauss's law, we get this form. Now using this vector calculus identity and Gauss's divergence theorem, we get this form. So here this del dot EV is basically divergence of VE minus E dot grad V. So that is why the first term is the total volume integration minus E dot grad V. And here first we will get the total volume integration, divergence, this one divergence VE, right? So total volume integration divergence VE. Then we use Gauss's divergence theorem. Then we get closed surface integration V. Right? Now using electric field is minus of gradient of potential, we get this form. So here this S is the surface which encloses the volume, this tilted V. Okay. Now from this form, it is clear that we should integrate over the region where the charge is located. But what will happen if we enlarge the volume beyond the minimum necessary to trap all the charges? So for that, let us consider the volume expands to infinity. This is permissible because the energy is 0 wherever volume charge density is 0. So here the charge density is 0, so that's why the energy will be 0. So that's why this is permissible. Now at large distances from the charge distribution, potential falls off 1 by r and electric field falls off as 1 by r square, while the surface area grows like r square. So roughly speaking, the surface integral goes down like 1 by r. So the volume, and you know the volume integral electric field squared, this term only increases. So at large distances, in this expression, if we go large distance, means if we cover the all space, in that case this second term becomes 0, right? So here you can see this second term becomes 0 and we are left with this first term, which is epsilon naught by 2 volume integration over the all space electric field squared d tau. Okay, so this is the energy stored in the system. Now let's discuss one example, then you will understand how to use those formulas to find out the electrostatic energy of a system. So here the example is, we want to calculate the electrostatic energy of a uniformly charged spherical cell of total charge Q and radius capital R. So here we will solve this in two methods. In method 1, we will use this form of electrostatic energy for calculating the electrostatic energy, right? So here we have to use surface integration sigma v dA, because here we have spherical cell. We know that the potential at the surface of the spherical cell is this. Now putting this form, we get this equation. Here 1 by 4 pi epsilon naught Q by R is constant. So it will come out from the integration, and surface integration sigma dA is the total charge of the spherical cell, which is this Q. And we get the electrostatic energy of this form. Now in second method, we will use this form of electrostatic energy. Now inside the spherical cell, you know the electric field is 0, right? But outside we have finite electric field, and this is the form of the electric field, right? Now using this form in the volume integration, we have to use the form of volume element in spherical coordinate, because we are considering a spherical cell and we get this form. Here the volume element d tau is basically r square sin theta dr d theta d phi, and the integration limit for r is capital R to infinity, because only contribution here is coming from outside the spherical cell. Okay, so only contribution in energy comes from the outside of the spherical cell. That's why we are taking R to infinity. Now here the integration sin theta d phi with proper limit will give us 4 pi. Now what will be the limit for theta? That will be 0 to pi. For phi, that will be 0 to 2 pi. And if we do the integration, it will give us 4 pi. And after solving, the final form of the integration will be like this, and we get this form. Thus we can see that we are getting the same form of electrostatic energy using the first method and second method. Okay, so this is all about electrostatic energy for discrete and continuous charge distribution, and you have understood how to use those formulas to find out the electrostatic energy for any charge distribution. Now today I am ending here. In the next class I will discuss some basic properties of conductors. Okay, thank you.